Hey, Dr. B here. Let's take a look at crystalline solids and predict some of their properties. You've seen them, salt crystals, a diamond, things like that. Crystalline in nature. First thing I think of is they're highly pure, and there's four main types. Perhaps you can guess from these images the four we're talking about. I see here individual molecules, in this case ethanol molecules. These are molecular crystalline solids, plenty of them. I see here all positive charges and little dots that are electrons. I don't see plus minus. These do not look like salts to me. I think these are metals. We also have a nice lattice, but these are formal plus and minus. This could be sodium chloride. We're dealing with an ionic solid. And finally here, they're exactly the same, but black oftentimes implies carbon. In this case, it's a complete network of carbon atoms. And when it's tetrahedral like that, that's diamond. So this is a covalent network solid. Those are four types of crystalline solids. Let's predict some of their properties. I'll show you some images, guess what types of substances we're dealing with, and maybe we can predict some properties. Okay, let's begin. This thing looks like it's going to be neon. That looks like it's going to be methane. The types of solids, those are just individual atoms or molecules. We also added water here. Type of solid is molecular. And molecular is a bit of a misnomer since that's just individual atoms, but that means you have either individual atoms or molecules with nice formal intermolecular forces. But not very strong ones, right? This is certainly not like a diamond. The melting points and the boiling points are going to be very, very low. These typically will be gases to liquids at room temperature, but once you get a little bigger, I think these things will become solids at room temperature. The unit particles are either atoms or, more often, individual molecules. You'll have the solid lines and the dashed lines for both the bonds and the intermolecular forces. And their properties, well, could involve the entire organic world, so it's going to vary a lot. But they can be on the soft side. They can have relatively low melting points. There's no ions here, so they typically won't be conductive. And we're really comparing these properties to what they might be compared to salts and diamonds and things like that. Other examples are incredibly numerous if you're considering the entire organic world. But these are some typical properties of these molecular solids. Let's move on to these two. Do you recognize them? That's the old notation for Mercury. This is some kind of a metal ring, so I think we're dealing with metallic substances. And that happens to be tungsten right there, very hard metal. We have metallic bonds which can be very strong, and yet there's quite a variation in the melting points and boiling points. But I think it's safe to say that, hey, metals are typically solids at room temperature. Not surprising since you have that delocalized sea of electrons between these cations that would be formed when you lose an electron, which metals do oh so easily. And that gives them some pretty strong properties. I always like to point out that metallic bonds are a little unusual in that you're not obtaining any kind of noble gas configuration. They are pretty strong in and of themselves, but they're not gaining any sort of chemical stability. They still typically want to rust or lose electrons, some more than others. The unit particles must be those individual metallic atoms. First thing I think of properties is they're going to be conductive, since we can have electrons flowing throughout the lattice. Hardness is going to vary, and you can have very high conductivity, a lot of variation in terms of their hardness. Oh, and don't forget that they're malleable and ductile. There's no reason that you can't smack these things down, because it doesn't matter if that pile of atoms shifts a little bit, it's still the same thing. All metallic atoms are included here. So there you go. Another class looks like this, and here I'm seeing formal different colors. So I'm seeing plus minus, or a bottle where it's shown magnesium oxide, cesium chloride. These are ionic crystalline solids. Now here there's a formal plus minus attraction, and that's strong. So we're going to see almost always high melting and boiling points, solids typically at room temperature. Perhaps there's not exceptions to that. The unit particles are the ions. A metal ion connected to a non-metallic anion, almost always, rare exceptions. The anion or the cation might be polyatomic, like ammonium, for example, or a sulfate, for example. Properties, well, these things are going to be brittle. You do not want to shift their location. If you hammered on it and the location shift, this beautiful plus-minus arrangement might suddenly turn into all repulsive forces. So they're going to be hard. They're going to be brittle, which is a serious limitation in terms of construction. But interestingly, they can simply dissolve in water. They might melt at 2,000 degrees, but you just throw in water and they just fall apart into individual ions that form those relatively strong ion-dipole interactions. We're dealing with typical salts such as sodium chloride and others. And rare, but perhaps the most interesting group, are these beautiful network covalent solids, quartz, diamond, things like these. These are oftentimes coveted substances. I would say beautiful substances. Since it's a continuous lattice of non-metallic atoms, they have very high melting points and boiling points typically. Look at those numbers. Those are way up there. But notice we're not dealing with an overall clear trend because there's variation within all these groups. The unit particle are those individual non-metallic atoms, or in the case of quartz, molecules, and their properties, since it forms such a strong lattice, are typically very high melting points, very hard substances, but there's no real reason to expect them to be conductive. They are not losing electrons like metals do to form that delocalized sea of electrons. They are instead just forming nice covalent lattices that are throughout. So they are like very strong substances. And there's not a whole lot of them. Graphite, graphene, glass, diamond, fullerenes, things like that. Those are the covalent network substances. This is a look at crystalline solids.